Hi, I am Mohammad Sadri, postdoctoral researcher at TU Kaiserslautern, and this is one of my other videos regarding the ZYNQ device, eventually the ZYNQ device, and this one is about designing modules that contain AXI Stream Interfaces using pure RTL coding. In the previous video, I showed you how you can design modules with AXI Stream Interfaces using Vivado HLS. And in this video, I want to focus only on creating such modules through RTL Flow. We don't want to use Vivado HLS. And as I will discuss, there may be some reasons for doing that. Before we go any further, I want to notify that these videos are just hobby videos that I'm creating here in my free time, and they are not official. They are my own point of view regarding designing embedded systems using Xilinx ZYNQ device. So they may be wrong, I may have mistakes, and use these videos and these trainings at your own risk. But yet, I believe that through these videos I can transfer the experience that I have obtained during these 2 years regarding the ZYNQ device. So let's get started. In this lesson that I will divide the video into several parts. I will record the video part by part. In this lesson, we will create modules with AXI Stream plugs using pure RTL Flow, and then we will use that modules inside Vivado, and we will connect the modules to other modules inside Vivado, and we will do simulations inside Vivado, and using the Vivado environment we will do simulations on our AXI Stream subsystem that we develop, and we verify, or we evaluate, better to say, we evaluate the correctness of the functionality of our module. And then we create a complete architecture from the module who is the source of the data, to the modules, AXI Stream plugs that are processing the data, and then finally to the module which is responsible for receiving the AXI Stream interface and converting it into an AXI memory mapped interface, and then finally the ZYNQ PS. Since now I have talked about the ZYNQ architecture a little bit, you should have a clue of what is the ZYNQ PS and what are the AXI interfaces available in the ZYNQ PS. So I don't see any problem to use the ZYNQ PS inside my design. Okay, so why someone may like to still use pure RTL Flow instead of HLS? As I showed you, and as you can see for yourself, the HLS flow is really fast, and it is flexible, and is really capable of realizing your design, complicated designs. And so for many designs you may think, okay, using HLS flow is better and is faster, and we can gain the results in a smaller amount of time. But at the same time, maybe you don't have access to the license of this HLS ZYNQ. Maybe it is expensive, and for example your university has not purchased that license, you don't have access to it. Or even sometimes you have access to the tool, but the design itself is so critical, I would say, and is so complicated or so constrained in terms of timing, is so constrained that you prefer to directly code in RTL instead of HLS. Looking at the old days of designing programs for computers, sometimes you were preferring to directly code in assembly instead of writing the C code, because for some specific portions of the code that you develop, you want to have everything completely under your control. And this is again the story with RTL and HLS. When you are using the HLS flow, in fact, you have one conversion level between the code that you are writing and the logic that is being created. When you use the RTL flow, you are more near to the final hardware which is going to be created. So when you code directly in Verilog or VHDL, RTL, then at the time of designing, at the time of coding, you have more control on what type of hardware is going to be realized after you create your module. While in HLS, your control is at a lower level. Now suppose that you are responsible for designing a module which should do a kind of processing on a stream of data with a latency of, for example, not more than 5 clock cycles. So you have a very tight constraint, and your design should be so that you meet this constraint. And sometimes going with HLS cannot indeed help us to achieve the constraint. Sometimes if I receive this task, if I try to code it in HLS, the final code that I create in HLS is practically more complicated than the code that I write in RTL. Sometimes for this type of very complicated problems, sometimes if you try to solve it with HLS, you see that the complexity of your code in HLS can become higher than the complexity of the code if you directly write it in RTL. So if you are trying to solve a problem and design a module, if it is something that you should have vision over every specific detail of the design, then maybe HLS is not a good option, because at the end the HLS will take your C code and will implement it in a way. Of course, the parameters that you give to the HLS tool, from they can really control the behavior of the tool on what type of hardware it generates out of your C code. But at the end, sometimes maybe it is better to directly code in RTL. In my view, the best thing that we can do is a mixture of RTL and HLS. For normal modules, for modules that do simple processing tasks or specific processing tasks, and they are not really complicated, and there are no tight constraints, then the HLS is awesome. It's perfect. It's really fast. And so the thing that you do in RTL, for example, for 5 hours, in HLS, it is 10 minutes, it is 15 minutes, you do the same. Especially just suppose with yourself that just imagine you are dealing with floating point, for example, calculations, and your module should handle floating point numbers, and at each stage of your pipeline, your processing pipeline, you have a different precision. And if you directly want to code these things in RTL, it's really time consuming, while in HLS it's really fast. But at the same time, for some specific parts of the code, maybe it's still better to code in RTL instead of HLS. Okay, what we want to do today is we want to create basically this block. This block is called sample generator, and what does it do? It doesn't do anything. It just contains an internal counter and it produces an AXI stream data over AXI port, which is a master AXI stream port, and the data will be the outputs of this counter. And it also has one slave AXI stream interface, and through AXI_EN port you can control if the output of AXI port is the output of the counter, or the output of AXI port is in fact the data that we have received through the AXI port. Okay, so with this AXI_EN, I want to be able to decide if I directly pass this AXI port to AXI, or I pass the counter which I have internal into this module, I pass the output of this counter on the AXI port. Okay, so and then we have the frame size. I will introduce to you for the AXI interface that we have here a new signal that is called T-last, and this T-last is indicator of the end of each frame, because in many situations the data that you transfer between AXI stream modules, it is grouped in frames. For example, if you look at an image, a video frame, if you look at a video frame, it has a start of frame, then each line has an end of line, and finally we have end of frame. And if I am transferring a kind of video frame between two AXI stream modules, then we need some additional signals between these modules to indicate the end of line at least and the end of frame. And we are going to talk about this in more detail. So I have frame size, and the frame size is a number, and this number is indicating number of samples that I have in each frame that I am generating here on AXI. And this frame size is used only and only when I am passing the output of the counter on AXI port. Okay, and then I have the enable signal, which is a global enable signal, and when it is 0 on AXI port, we don't want to see anything. We don't want to see any activity, so it disables the module completely. This is the module that we are going to design in RTL, and then what I am going to do is that I'm going to instantiate this module in a complete processing pipeline. So what does the complete processing pipeline contain? It contains our module. Then I intentionally want to show you how you transfer from one clock domain in your design to another clock domain. For example, you have an A to D. It is connected to your ZYNQ device, and the A to D is operating, for example, at 50 MHz, while inside the ZYNQ device your processing system is running at 250 MHz. How do you transfer data between the 50 MHz clock domain to the 250 MHz clock domain? Here is the solution, and a stream asynchronous FIFO. So intentionally in our sample design, we will instantiate this module and we will see together how we can use it. Then the output of asynchronous FIFO is connected to an AXI FFT module, which is again a ZYNQ block. So this asynchronous FIFO and this FFT module, and these modules here, they are all ZYNQ blocks, and this is the only block that we have created ourselves. The FFT block is again a ZYNQ block, and what it does, it receives your frame, the frame of samples, and on this frame it calculates the FFT, the fast Fourier transform, and then it outputs the coefficients on its AXI stream port. So here the stream that we see here are actually the coefficients of the FFT calculation, the coefficients that are obtained through the FFT calculation. Then these coefficients, these numbers, just numbers. They enter the module which is performing a very important task. It is called AXI DMA. The AXI DMA, as I will show you, is responsible for receiving your AXI stream data and then passing them through an AXI memory mapped interface to the ZYNQ PS. As I told you in a previous video, the AXI ports that we have on the ZYNQ PS, they are all AXI memory mapped ports. We don't have any AXI stream port on the ZYNQ PS. And when you want to transfer data from the PL to the PS, then you have to pass the data to the PS through one of these AXI memory mapped ports. So what we are doing here is that we use the AXI DMA module, and the AXI DMA module will receive the AXI stream data and will put the data on the DRAM here through the AXI memory mapped interface that we have here. So I will connect, in fact, the AXI memory mapped master port of AXI DMA module to one of the AXI memory mapped slave ports of the PS, for example HP0, and then through this port I will write the data that I receive on this port here. I will write this data to a specific location in the DRAM, and then later, for example, what you can do after the data is written here through the ARM CPU cores that you have here, you can perform some additional processing on the data. Or for example, you can packet them and send them through Ethernet. Or for example, you can store them on the SD card that you have on the ZYNQ board. So there are a lot of things you can do using this data, and it's, I think, representative of a example signal processing pipeline that you may ever implement on the ZYNQ device. Okay, here we are in the middle of the video, and probably I will repeat this many times. I would maybe the thanks part I will do later. Just all of the videos of these lessons, you can find them on my own websites, greenelectrons.com and googlia.com. This is part 1 of this session. So this session contains several parts, and for each part I create one specific video. Thanks for watching. See you in the next section of this course.